is about obtaining the primitives of rational functions. Okay. So if you remember, rational functions are of the type R, where R is equal to P divided by Q, where P and Q are both polynomials. Okay, and we can focus on those functions R where the degree of P is smaller than the degree of Q, right? And the reason for this is that the degree, suppose the degree of P is greater than the degree or equal to the degree of Q, then we can always divide P by Q, and so we can get a polynomial expression plus another polynomial m divided by Q, which is the remainder, right? And so if we want to compute the primitive of this is going to be just the primitive of a polynomial, which we know how to compute, and the primitive of this rational function. Okay, so it doesn't matter what degree of the original rational function, we can always transform it into a rational function where the degree of the numerator is smaller than the degree of the denominator. Okay, now how do we deal with this? Well, if we have the denominator, so let me write it here, right? This is R is P divided by Q, right? Well, the denominator is a polynomial, and we can always factor polynomials according to the roots. Okay, so it's going to be x minus a1 to the n1, okay, where n1 is the multiplicity of this root. Okay, so for instance, whenever you have, for instance, I don't know, x squared minus 4, right? No, sorry. You have x squared minus 2x plus 1, right? This is equal to x minus 1 squared, right? Now that means that this polynomial, right, can be factored into the product of x minus 1 two times, because the root 1 appears two times. Okay, so every polynomial can be factored according to the product of its roots, right? X minus the roots, where this goes up to this, and then there's some polynomials that don't have roots, like for instance something like this, p1 x plus q1 to the m1, right? So for instance, you could have x squared plus 1, for instance, right? There is no real root for this, so you cannot express this in this simple form, right? And you can have as many as you want of these factors, right? You could have x squared plus p2x plus q2 m2 blah 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 up until s of this, for instance. Okay, s. Okay, so you can always factor this polynomial into this kind of factorization with regards to the roots, right? Now, if we have this, right, in the denominator, a product of things, we know we can always separate the factors, right? And so if we have any rational function like this, we will be able to express it in terms of this let's say factors according to the multiplicities. Okay, so it's going to be something like a1 divided by x minus a1 plus a2 divided by x minus a1 squared plus, and then up to the multiplicity a sub n1 divided by x minus a1 to the n1. Okay, that's just the first factor, and then the same thing with the second factor, b1 x minus x a2 to the 1 plus b2 x minus a2 squared, and so on and so forth. Okay, bn2, okay, n2 factors here, x minus a2 n2. Okay, and that for all the simple factors it works the same, right? And now with these factors we have similar, it's a bit more complicated. It's c1x plus d1 divided by x squared plus p1 x plus q1, and then c2x plus d2 divided by x squared plus x plus q1 squared, okay, plus blah blah blah, plus all the factors that you have m1, so cm1 x plus dm1 divided by x squared plus p m1 x, sorry, see, this is p1 again, sorry, plus p1x plus q1 2dm1. Okay, so its factor appears in the composition as many times as its multiplicity, right? And so you can do that with all the factors. Okay, so